Hi guys, welcome back. In this video, I'm going to talk about a dual loop circuit with a voltage source here. You see that I have an inductor here, a capacitor, and two resistors, R1 and R2. So let's go ahead and do the four-step approach for this problem. Okay, I'm going to start with step 1, which is basically listing the elements in the system. So I'm going to have it as inertia, stiffness, friction, my sources, and I would comment on the number of ODEs. Okay, looking at this system, you see that I have only one inertia element. And if you guys remember, inertia elements in electrical systems were the inductors. So I have only one inductor. I'm gonna put it as L there. Also, I have only one capacitor, C, that's gonna be my stiffness element. For friction, I have two resistors, R1, R2. So let's put them here. The source in this problem is the input voltage, which I'm going to show it with En or E sub n. And also for the number of ODEs, if you guys remember, we looked at the number of energy storing elements. We have one inductor and one capacitor. So 1 plus 1, I would need 2 ODEs. Okay. Let's go to a step 2, which is our dynamic variables. For dynamic variables in electrical systems, you look at either the voltage across the capacitors or the currents through the inductors. So EC and IL are your dynamic variables. With this, I'm ready to go to step 3, which is writing down the two ODEs for the energy storing elements. Yes, so one ODE for the capacitor and one ODE for the inductor. So write down two ODEs, okay, or let's say ODEs for your energy storing elements. Okay, so let's go ahead and write down the energy storing elements, the ODEs for them. Okay, so I would have EL equals to L I dot L, and also I would have C E dot C equals to IC. Okay, let's call this equation as equation Smiley. Let's call this equation as equation Cyclope. And what I'm going to do is, again, I'm going to go after good terms and not good terms. Again, to just refresh our memory, our good terms were either the inputs or the sources and my dynamic variables. Whatever that's not your input, that's not your dynamic variable, is not a good term. Okay. Just like the previous examples, I dot L is the time derivative of your dynamic variable, so that's a good term. EL is not your dynamic variable, it's not your input, you need to get rid of this guy, so this is not a good term. What do you guys think about E dot C? Well, okay, EC is your dynamic variable, E dot C is the time derivative of it, so it sounds like it's a good term. And at last, IC is not your dynamic variable. It's not your input. It's not a good term. So you have to get rid of IC as well. Okay. So look at this. Your job from now on is getting rid of the not good terms, which are EL and IC, using three tools that you have in your toolbox. What are those three tools? KVL, KCL, and Ohm's law. So let's go to step 4. Okay. And rewrite the not good terms okay, using KVL, KCL, and Ohm's law. Okay, at this point, we are ready to go, yes? Okay, so let's go back and look at the problem setup one more time, okay? And I want to see what are my options, okay, for KVL, for KCL, and for Ohm's law. Okay, so let's have a broader view, okay, an overview to this problem. First of all, I would like to ask you guys a question, okay? How many KVLs can you write for this problem? Okay, it sounds like you have one loop here, okay, and you have another loop here. Yeah, so in general, you can have 2 KVLs. Yes? How many KCLs you can write? Well, okay, you have one node here and one node here. So in total, you can write 2 KCLs. However, if you call the node down below here as B, you see that node A on the top and node B on the bottom are somehow similar. Yes? If you write the KCL for node A and multiply that KCL by -1, you will get the KCL for node B. So there is no need to write the KCL for node B. Just one node, and that's node A. So you have one KCL. Yes? And also, you can write Ohm's law for R1 and R2. So you have 2 of these guys. Yes? So you have 2 of Ohm's laws. So at this point, you guys know that for the first one, you are going to multiply R1 value with the I that passes through R1, which is I1. For the second one, you know that you're going to multiply R2 by the I that passes through it, which is IL. Yes? And anytime in your KVL, okay, that you see such a thing that you have ER, okay, you can go ahead and use the Ohm's law automatically. Yes? So let's go back to step 4 now, okay, and see what we can do. Okay, so for the KVL on the left loop, okay, which I'm going to call this loop over here as the left loop and this loop over here as the right loop. Yes, so for the KVL for the left loop, I can start walking on the circuit. Yes, so let's go ahead and imagine that this is me, and I am going to go and walk in this direction. Yes? So using convention 1, since I am moving in the same direction of the current I1 across R1, you guys know that the voltage across R1 drops. Similarly, because when I get here, I use in the same direction of the current IC, the voltage across C also drops. And at last, when I get to the battery, I hit the negative polarity of the battery first, and the voltage across the battery rises. Yes? So this was convention 2. Let's write it down here. Negative ER1, negative EC plus EN equal to 0. Yes? And you guys have right now a pretty good idea that, well, you can rewrite this ER1 using the Ohm's law. Yes? So let me just go back and do the substitutions at the end. Now, let's go to the KVL on the right loop. So on the right, and on the left. Just cram to each other here on the left loop. Okay, so similarly, at this point, imagine that I am the blue guy right now. Yes, and I'm gonna walk on this circuit in the direction that I show you. Across the inductor, you see that the voltage drops. Why? Because of the first convention. I am moving in the same direction of the current IL. And if you notice, across R2 also, the voltage drops because R2 and L are actually sharing the same current IL. Yes? When I get to the capacitor at this time, since I'm moving against direction of the current, you guys know that the voltage rises. So if you want to write it down as negative EL, negative ER2 plus EC equal to 0. So they are my two KVLs, yes? And you guys at this point have a pretty good idea that ER2, you can substitute it from the Ohm's law, yes? Okay. Now, let's look at the KCL that we have, okay? For the KCL, if you look at the node A, you notice that I1 enters this node, IC and IL, they leave the node, yes? So I1 comes in as positive and IC and IL leaves as negative, yes? So this is gonna be I1, negative IC, negative IL equal to 0. Yes? Good. Now at the end, I have the two Ohm's laws, yes? So you guys know that ER1, so let's say Ohm's law first, yes? Ohm's law, okay? You have ER1 equals to R1, the current that passes through R1. If you guys notice here, the current that passes through R1 is I1. Similarly, the current that passes through R2 is IL, the same current that passes through the inductor, since these two guys are in series. Yes? Okay. So let's go back here, and it's going to be R1, I1, and also here it's going to be ER2 equal to R2, I2. Good? Okay, nice. So once again, let's look at your step 3, okay, and refresh our memory. What are we looking for? Well, we are looking to rewrite EL and IC in terms of our good terms. What are our good terms? Our dynamic variables and our input. Yes? Okay. Now, let's look at this. One of them is pretty simple, yes? So you can simply, the first thing that you would do is you can simply go ahead and substitute for ER1 here, okay, and for ER2 here, okay? So this should be IL, okay, ER2 here. Now, if you do that with these substitutions, okay, you will get negative R1, I1, negative EC plus EN equal to 0. Yes? Similarly, if you substitute ER2 in the second equation, you get negative EL, negative R2 IL, yes, plus EC equal to 0. Yes? And at last, from the third equation, it sounds like you have I1, negative IC, negative IL equal to 0. Okay. Now, my friends, look at this. You have 3 equations, and in these 3 equations, your EC is a good term. It's your dynamic variable. EN is a good term. Yes. So EC here is a good term. IL is a good term. It's your dynamic variable. Okay. And Here also IL is a good term. So they are your known, they are your good terms. The ones that are not good or they are unknown to you per se, yes, are one I1, EL, okay, and IC. So you have three equations and you have three unknowns. What are your unknowns? Your unknowns are I1, EL, and IC. Can you write this system of equations for these three unknowns? Of course you can. The easiest way to solve this system of equations is through substitution. Yes? So, first of all, let me just copy these three equations down below and start working on them. Yes? So, I'm going to copy these equations, okay, from here to here. So, just have a little bit more room. Okay. Now, look at this. What did I wanted to find? Again, IC, EL, and I1. Look at this. From the second equation, I can easily find EL in terms of my good terms. So my EL is in fact equals to EC minus R2 IL. Look at this. EC is a good term. It's my dynamic variable. And then IL is also a good term. It's my dynamic variable. Yes? So you can easily go ahead and substitute this equation. I would call it as equation 1, okay, into equation smiley here, okay, and you're done with that equation. The next thing that you need to take care of it is IC. Yes? If you look at this problem, you can find the value for IC from the third equation here. Yes? So your IC would be, in fact, I1 minus IL. In this equation, you notice that IL is your dynamic variable. It's a good term. Yes? Your I1 is not a good term. However, you can find the value for I1 from the first equation and substitute it here. Yes? So if you go ahead and solve the first equation for I1, you see that your I1 is equal to 1 over R1 En minus EC. Yes? And you notice that in this equation, both EC and En are good terms, and R1 is a constant number. So you were able to find or solve I1 in terms of your good terms. And when you go ahead and substitute I1 here, you are done with this equation. So by substituting I1 as 1 over R1 En minus EC minus IL, you are right now able to represent IC in terms of all your good terms. En is a good term, EC is a good term, IL is a good term. Why? Because En is your input, EC is your dynamic variable, and IL is your dynamic variable too. Okay, so I'm going to call this equation as equation 2. Yes? With 1 and 2 equations, Smiley and Cyclope, I can go ahead and rewrite my dynamics. So substitute first equation 1 in equation Smiley. Okay, what do you get? Equation Smiley was EL equals to L I dot L. Yes? Instead of EL, you're going to substitute from equation 1, which is EC minus R2 IL. Yes? So instead of EL, I'm going to put it as EC minus R2 IL. Yes? Okay, with this, let's bring all the dynamic terms on one side, okay, and check for the signs. If the signs match, we can box that equation. So L I dot L equals to, L I dot L plus R2 IL minus EC, this is equal to 0. I just brought the left-hand side to the right-hand side, and then I flip the sign. So Look at this. How many families do you see in this problem, in this equation? Well, I see two families, family of IL and family of EC. In the family of IL, I have two members, IL and IL dot, these two. No sign changes within the family of IL. And for family of EC, I have only one member. So I can go ahead and safely box this equation. This is one of my differential equations, one of the ODEs. For the next one, I would do very similar. Yes, I would substitute equation 2, which was the equation for IC. If you guys look at this one, the equation for IC here in the cyclope equation. Okay, so what was cyclope? That was the equation for the capacitor. Yes, so let's go ahead and rewrite cyclope here. Okay, so C E dot C is gonna be equal to IC. Yes, now I'm gonna go ahead and instead of this IC here, yes, I'm gonna write equation 2. So let's go to equation 2. Okay, and it's gonna be 1 over R1 En minus EC, all of it minus IL. So it's gonna be 1 over R1 En minus EC, all of it minus IL. Yes? Okay, just make sure that I'm not making any mistakes. Yes. Okay, perfect. Now I'm going to do the same thing, the same thing. Okay, so one thing that I can do to just make it look a little bit nicer, I can multiply both sides of this equation by R1 to get rid of the R1 in the denominator. Yes, so if you multiply both sides by R1, you will have R1 C E dot C equals to En minus EC minus R1 IL. Yes? Okay. Now look at this. Right now, these two terms on the right-hand side are dynamic terms. Okay. I'll bring them to the other side. Okay. And flip their signs. Keep the input on one side. So it's going to be R1 C E dot C plus EC plus R1 IL equals to En. Now, check for the signs. If the signs match, then you can box this equation. Okay, my sanity check. Yes, I have two families, family of EC and family of IL. Within the family of EC, I have two members, EC and EC dot. Within the family of IL, only one member. You see that I do not have any sign changes among the members of families. Yes, so I can safely box this equation and represent it as our ODE. Thank you.